So now we're going to come to the fun stuff, the great stuff, gravitational waves, what they really are. So gravitational waves are basically ripples in the fabric of space-time. Now scientifically, this is by changing the quadruple moment of mass distribution. Basically, in layman's terms, it means when there's an asymmetrical change in anything, gravitational waves are produced. Me walking is producing gravitational waves. Cars, planes, all of them produce gravitational waves. But they're so small, it is literally not even worth trying to detect them. However, these type of gravitational waves, called stochastic gravitational waves, once again, which I will be coming into in the end, they play the biggest role in understanding what really happened during the Big Bang. So one thing I really want to explain to you really when I say ripples in the fabric of space-time is what space-time really is. Because as I mentioned, Einstein's field equations is also one category that I'm going to be talking about. So the first and major thing that people kind of fumble on is, well, what is space-time? We know space, we know time, we can say flat space or Euclidean space where everything is flat. But what happens when you curve them together? What happens when it's a single continuum? And how is it really a single continuum? The answer is Pythagorean Theorem. Literally, something we learned in grade 6, I'm going to say 6, I don't know. A pretty early grade, a pretty early 7, a pretty 8, a pretty early grade. Pythagorean Theorem can really define everything that we know about gravitational waves and the curvature of space. Why? Because Pythagorean Theorem, the way Pythagorean Theorem has conformed on the manifold, which I'm going to be showing you by the way, actually can tell us the curvature of the manifold. So here we have Pythagorean Theorem. I think all of us should know this by now, where instead of representing ABC, I'm representing differentials because, you know, we're talking about calculus a bit here, and we're talking about very, very, very minute changes. So I'm going to be referring to x1 and x2 and x3 because, as you know, there are more numbers than letters or alphabets, and therefore we're going to be working with x to the first, or x1, x2, x3. Many people sometimes disregard this for power, like x2 squared, they think it's x to the fourth. I know it's a bit confusing, but just think about it because these are going to be contravariant, and because they're contravariant, we're actually working with the number of dimension. You can think of it as dimensions. So now one thing that you might be seeing is that this works perfectly fine, but what happens in curved space or a spherical coordinate system? Well, that's right here. So in a spherical coordinate system, as you can see, the circle is really badly drawn, but in a spherical coordinate system, the lines aren't even straight, because if you kind of visualize it, not very good to draw it, if you can visualize a sphere and a triangle drawn on it, you're not going to really visualize straight lines. All of them are going to be curved. So how much are those lines curved will tell us, as I mentioned, the curvature of the manifold. Before we go any further, I do want to write another equation because we can be working with various dimensions. We can be working with 2 dimensions or 26 dimensions. So that's working with various dimensions in this situation. So that's once again starting off from where I started, and we're just summing up over all possible values. But once again, there can be 2 different variations of dimension because we are working with the x-plane and the y-plane and other dimensions going with it. So we're going to be doing x to the m into x to the n. Now, m and n, by the way, are summation terms. Einstein, however, it's actually a pretty interesting fact. Einstein, in his papers, he did not include a summation term because he said that the summation term was implied. So I've actually included them in a lot of my equations. If I haven't, I will tell you. But a lot of my equations, I've just included the summation term because it's easier to understand what it's really trying to say. And this right here, that is the Kronecker delta. The Kronecker delta is sort of like a function that equals 1 when m equals n, and equals 0 when m does not equal n. The reason for this is to make sure, remember Pythagorean Theorem is a squared equals b squared plus c squared. So both of them have to be squares, and therefore both of the powers have to be the same power. Hence, we have the quantity delta over there to make sure, 100% sure, that the powers are actually going to be similar. Now, one thing you might have also noticed, this is only working with one frame of reference. And that is a problem, because as you might know, relativity, the literal word, means that everything is relative. Hence, we cannot only be working with one dimension, one frame of reference, we can be working with various frames of reference.
So that is an extension of Pythagorean Theorem.
Exactly.
On an n-dimensional sphere.
On an n-dimensional flat space. I haven't come to curved space yet. Flat space. Yeah, by the way, sorry, I didn't mention that. This is flat space. I'm going to be coming into curved space in 3 slides. So this is flat space, not curved space. That's very important. So now we're going to be getting into different frames of references. Now the next equation might not seem very relevant, but you will understand why it's important. So as I mentioned in the beginning, tensor analysis is important to understand what it really is. Don't worry if you don't, I'm here for that. So this is the covariant tensor transformation. I could put contravariant tensor transformation, but covariance is easier because it's actually utilizing the dot product of the vectors, or in this case, the tensors. So over here, once again, we have a simple summation term, and now we actually have 2 frames of references, where y is one frame and x is another. So this is, in this situation, we're converting from one frame of reference to another frame of reference of a tensor. So now you might be wondering, wait a minute, what's a tensor? So as we might know, scalars and vectors, we already know what those are. Scalars are tensors of rank 0. Vectors are tensors of rank 1. And then we get the matrices, which are tensors of rank 2, linear algebra. Then we get into 3-dimensional matrices, which are, so basically we're just going higher and higher tensor analysis. And once again, this is not really the goal of today's presentation, tensor analysis, but I just wanted to show you that changing frames of references is very important for when we come into the curved space analogy and when we understand Pythagorean Theorem in curved space. So M and N, once again, are the original summation terms, and R and S are the new summation terms. So it's a little bit confusing. As I mentioned, Einstein dropped the summation term entirely, so I've at least tried to include it in some ways possible so you can sort of get an intuition of it, but basically what's happening is these 2 summation terms work with your other frame. Because one thing you have, yeah, sure.
Is that an R?
Right there, yeah, it's an R. Isn't that right? Sorry. Okay, so one thing you have to remember is, okay, you know what? If you don't mind, I should not regret myself. Okay, so let's say we have, okay, that's a terrible eraser, huh? Yeah. Sorry, do excuse me. Okay, so let's say I have a field, a vector field, a tensor field, and I have my x, y regular planes. Now this might be, now technically you might be thinking x and y mean x and y, but that's not what it means. Once again, very confusing because the variables, what's actually more confusing in this equation isn't the equation, but it's the variables and how they're used. So this is not x and y, no. This is still x1 and x2. Y is a totally another frame of reference. Like, let's say this. This will be frame of reference y. Let's say y1 and y2. Now, yeah, I know, it might be confusing to understand which one is actually which, but always remember in Einstein field equations, if you ever see an xy, it does not mean x and y. It actually means 2 completely different frames of references. Because as I mentioned, the main purpose of relativity is to prove that everything is relative. Hence, everything will stand true even if you change your frame of reference. Now these are simply taking partial derivatives of the function itself, and if you want to change this to a contravariant tensor, that's perfectly fine. You just swap the differentials because, as you might know, contravariant tensors are different from covariant tensors in the sense that contravariance is basically when the length of the vector or the coordinate is directly proportional to the basis, and covariant is exactly the opposite. So let me just explain myself because I think even I lost myself there. So let's say we have a graph and we have some tensor, whatever. Now, This is simply a vector quantity, but let's say it's some random vector right there. What a covariant means is that when we have, so these are our bases, so these are our bases right here. This and this would be our basis, and we have our vector right there. So in covariance, this is going to be constituent of the different basis vectors. Let's say we have this, we have 1 and 2 and whatever. So you have one of this vector right here and one of the x2 vector right there to actually make up this vector right here. So this is when you talk about covariance, when these are both directly proportional to one another. But in contravariance, we're actually working with the exact opposite. When the object, the coordinates of the object change inversely to the change in base. Was that confusing?
Yes.
Yes, okay, yeah, because and once again, I think I'm really confusing myself more than I'm confusing you. So let's explain that a little bit better, hopefully. So let's say we have a basis, right? We have our base vectors right here, and we have, once again, whatever vector. Hopefully I explained it a little bit differently this time. So let's say we're changing from 1 meter to 100 centimeters, right? We're changing length of our base. This will actually change even more because the coordinates are changing. So what a tensor really means is that the coordinates of the vector will experience a change either directly or inversely proportional to the change of the base, depending on covariance or contravariance. In this case, it's covariance. However, the object itself is invariant to change, which is a definition of a tensor. So the object will not change, the length will not change, but the coordinates, depending on the basis, will change. Now, that explanation, the reason I didn't say directly or inversely, because that depends if we're working with a covariant tensor or a contravariant tensor. So sure, it does get a little bit harder when you go into tensor analysis and understanding the different types of tensors, but hopefully I made it a little bit simple.
Okay. So how is it that the length doesn't change but the coordinates change?
So what that basically means is, as I mentioned, let's say I have 1 meter, right? I change it to 100 centimeters. The coordinates change from 1 to 100. But the length of the vector doesn't change. 100 centimeters still equals 1 meter, right? But the coordinate will experience a change under change of basis. Okay, hopefully that kind of made sense. Once again, we're not really studying tensor analysis, but it's very important to understand the different frames of references before we actually go into the biggest tensor of them all. It's really cool. So once again, let's just get back to the equation that we once derived, sort of derived, which is Pythagorean Theorem in flat space. So what do we do when we're converting it to curved space? Now the next equation is actually an equation. I could show you the derivation, but once again, it might take more time than is allotted to me. But once again, I do have the half an hour, so I could explain it then. But what we're doing now is we're multiplying it by my favorite tensor, the metric tensor. Okay. So the metric tensor is basically the basis for curvature. If you want to convert something flat into something curved, you multiply it by the metric tensor. In this situation, once again, as you can see, this is exactly like a covariant tensor transformation. This is basically the same thing, right? As you can see, I've literally used the same variables as well. So it's very similar to a covariant tensor transformation. And this is, once again, our two differentials that we worked with in the beginning, right? When we had Pythagorean Theorem, we have the two differentials over there, and we have the metric tensor over here being summed over RNS. Once again, if you actually see Einstein's field equations, you will not see these, but I thought not to be lazy, and I can actually do it. Okay, I wasn't calling Einstein lazy. So, once again, you can see the Kronecker delta just to make sure that Pythagorean Theorem holds in curved space and flat space, and it holds for all situations, whatever your nth dimension. Okay, so Now we actually get a little bit into the metric tensor, because that, my friends, is the base of literally curvature. So the metric tensor in this situation, as you can see, is being summed over m and n. Now I actually did forget that the summation terms m and n are also to be included. So there will be 4 summation terms here. Yeah, as I mentioned, he dropped it entirely, so it's pretty simple right now, but he completely dropped it in his papers. So, yeah.
Okay, so like you have these 2 sums, but you also have this Kronecker delta.
Sorry?
You have these 2 sums, but you also have this Kronecker delta.
Yes.
Shouldn't
Yes,
that,
you do.
Shouldn't that destroy one of the sums?
Because this is, sorry?
Shouldn't that get rid of one of the sums, the Kronecker delta?
Why would it? This is, Kronecker delta, once again, is like a simple function.
Yeah.
It's just like a function that equals 1 when, once again, n equals n equals 0 when n does not equal n, to make sure that these two do not overlap.
Or an S or anything like that.
Yeah, I know, exactly. That's what I mentioned. It is pretty confusing, which is actually being summed over. So technically, there would be 2 more summation terms included. It's very convenient that I'm realizing this now. But there are 2 more summation terms included, which would be m and n over there, because we're, as I mentioned, summing over all possible dimensions, including the different frames of references. Right? So m and n are used in this situation because I'm just working with spatial dimensions, right? I'm not getting into time. But as we know, as we all know, Einstein's field equations, we need time. So we work with 2 different variables, because physicists love Greek, right? So instead of m and n, they use mu and nu. So we have this right here. So this is your time, your space-time definition. Remember I told you in the beginning, I want to rigorously define space-time right here. So mu and nu, as I mentioned, are our 2 variables here. This is a simple 4x4 square matrix, which is a tensor, hence the metric tensor. If it was a column vector or a row vector, it would be a vector, or if it's just a number, it's a scalar. So in this situation, it's going to be a 4x4 matrix that you can see right here, and mu and nu is used. Now, if I'm not mistaken, in the further equations, I will be using mu and nu, but if I don't, do remember that mu and nu work with time coordinates as well as spatial coordinates, and well, our regular m and n only works with spatial coordinates. So now let's, hopefully we understood what space-time really is. I know that I've taken a lot of time to actually define space-time itself, but as I promised you, Einstein's field equations were going to be in there, and this is where we're starting. We're basically starting to derive Einstein's field equations. So now we're going to be diving a little bit deeper into gravitational waves themselves. Because right now, all I've been really doing is defining space-time. I haven't really got into gravity, I haven't really gotten into curvature, I haven't really got into a lot of the things that I should have been getting into 32 minutes in my presentation. But do not worry. Do not worry. Things have been planned. So gravitational waves was proposed by Henry Poincaré in 1905. And 10 years later, as we know, general relativity was not only proposed, but actually, no, proved in 1919. Yeah, it was proved in 1919. Yeah.
No, sorry, go ahead.
Oh, sorry. So general relativity was proved in 1919 by a group of astronomers that actually saw gravitational lensing. Why? Well, let's give it a moment. So Einstein thought, let's say I'm on Earth. Let's say I'm in a box. I can't see anything. I don't know anything. I'm in this one box, restricted, it's completely dark. And I'm obviously undergoing an acceleration of g. In this situation, I'm in a rocket somewhere in space, traveling upwards at g. Einstein said that the person inside will not be able to tell the difference in this situation and in this situation. And this is known as the principle of equivalence. Understanding that this and this are basically the same thing. However, if you think a little bit deeper, there are loopholes around the principle of equivalence. Because if you think about it, there is a very small change in tidal force over here and over there. So there's a very small, minute change. So technically speaking, you could very, very minutely actually tell the difference. But generally speaking, even though there was this loophole, the fact that these people would not experience anything different. That's really what's to be said. Not the fact that they can't tell the difference, but they will not experience anything different is known as the principle of equivalence. So this was his first predicted thought experiment, and then his second thought experiment was gravitational lensing. If you think about it, right, by Newtonian mechanics, we know that F equals gmm over r squared. It's a pretty, it's a formula stuck in our head by now, and we know that gravitational lensing occurs, where light is actually bent in a gravitational field. However, this is where things get weird, because if you plug in a photon's mass, which is 0, into F equals gmm over r squared, the entire force becomes 0. But obviously there isn't zero force, because we can actually measure the fact that there is gravitational lensing. So what is going on? And this is when Einstein really started to think about general relativity. As I mentioned, he had two thought experiments. The first one I just showed you, and this is the second one, gravitational lensing. This was proved in 1919 by a bunch of astronomers when there was a solar eclipse. They saw stars that they generally shouldn't, because it was exactly behind the sun. You should never see stars like that. However, they could, because number one, solar eclipse, therefore everything was dark except for the stars, and they could see two apparent positions. That just leading to the optical image of light and how we perceive light in straight lines and not in curves. But generally speaking, the fact that light curves in a gravitational field influenced Einstein to prove general relativity. So now you might be asking yourself another question, which is actually a pretty good one. Does curvature cause gravity, or does gravity cause curvature?
Gravity causes curvature.
Well, okay, fair enough. And any others? So intuitively speaking, that would be the answer, right? Gravity is the one that causes curvature. But then Einstein said, that's not right. Because I say that, wait a minute, gravity doesn't cause anything. It is the cause of something else. Newtonian mechanics proves that gravity is a force. Einstein proved that gravity isn't a force, it is a result of curvature. Now you might be asking, wait a minute, you're not making any sense. How can you prove this? Well, ladies and gentlemen, we are now going to get into the biggest part of the presentation, Einstein's field equations. So this is basically the field equations, where this is maybe the most important emphasis that I'm going to be applying on today, because what this represents is very important. This right over there, it actually changes if you're talking about gravity or if you're talking about light. Because if you're talking about light, this works with the 4 vector. If you're working with gravity, it works with the stress, energy, momentum tensor. Don't worry about all those gibberish words. I'm going to be explaining them in just a second. So this entire left side and this entire right side means something. And that's one thing that's not understood by many people. What does this really mean? I mean, sure, it's just a bunch of gibberish, but what does it mean? What are you trying to calculate? As I mentioned, we're trying to calculate curvature. And as we've understood, gravity is the result of curvature. But how can I prove that? Because the entire left side of this equation is curvature. This right here is known, once again, I am going to be showing you the formulas, by the way. Do not worry. This right here is known as the Ricci curvature. This right there is known as the Ricci scalar. The only difference is that this is a tensor while this is a scalar. Right over there, as you can see, my favorite tensor, the metric tensor. Right over there is the cosmological constant. Now this is actually a very important part of the entire equation, because so Einstein's first general relativity equations prove something pretty interesting, that the universe should be collapsing. But as we know by now, it's not. It's accelerating forward. And that is what that is trying to prove over there. The cosmological constant is just the scalar multiple of the metric tensor that multiplies out to state that the universe is expanding and not contracting. So this entire portion, once again, I will be explaining it, so don't worry, is basically looking at the momentum, energy, the flux, and stress of the object in question. So I don't even have to answer that question anymore, do I? Because the equation answered it for me. Curvature is related to mass, is related to momentum, is related to energy, not gravity. Gravity is what comes out of this right here. Because when you actually equate the stress energy momentum tensor, which once again I'm going to be showing you, it equates into gravity itself and what gravity is trying to tell it. So that's one thing we're going to be getting into as well.
So the moon goes around the Earth.
That's actually the next slide. That's amazing.
Because the Earth is causing a, what do you call it? A curve.
The coincidence is, it couldn't be
Yeah,
better.
like that.
It couldn't be better.
Okay.
So this right here is a sort of animation of the Earth with the moon revolving. Revolving with the moon revolving around the Earth. So in this situation, as we can see, there isn't a centripetal force or anything experienced by the moon, which is gravity. No, there is a curvature which is experienced. And that curvature is what really induces what we think is gravity. Now the Einstein field equation might seem very complex, but if you think about it, it's really not used very often. NASA doesn't use it, SpaceX doesn't use it, they don't use it because it's not right in situations where Newtonian mechanics can be used. What I mean by that is obviously general relativity isn't wrong, but Newtonian mechanics isn't wrong either. It is right to a certain extent. I'm going to be showing you the first proof of general relativity and what the field equation solved really looks like when we're going to be getting into the source-child metric and understanding what that means and how it's been transformed. But simplistically speaking, this curve is what really induces the gravity. And Newtonian mechanics is used over general relativity in most cases not because general relativity is too hard, but because it's pointless. It's proving something that we can already prove or deduce with Newtonian mechanics. As I mentioned, F equals gmm over r squared is not wrong. But the moment we're talking about photons, gluons, black holes, singularities, that's when stuff starts to break down in Newtonian mechanics, and it's just flat out wrong. And that is when you apply it in general relativity. So now I'm going to really be explaining the field equations in the entirety of the field equations here. I could be explaining a little bit more if you guys would like in the last half an hour. I'm just looking at one thing here. So really understanding the field equations and what they're trying to tell us is very important because as I mentioned, it might seem very complex. It is, but the curvature being related to the momentum, flux, energy, stress is the key of understanding the definition of Einstein field equations. So this right here, as I mentioned, is the Ricci curvature, which is a tensor. This right here is a commutator of a covariant derivative. Oh, big words. Basically, a covariant derivative is simply used to transform a regular derivative, or in this case, a partial derivative, to curved space. I actually saw that a lot of you have done covariant derivatives, so this will be nice. So this right here, if you haven't seen, is known as the Christoffel symbol, which I am going to be defining on the next slide. So if you don't understand that, don't worry, I will be defining it. And this is simply working with the partial derivative. This is, by the way, d over dx. I just haven't written it because, once again, Einstein dropped a lot of the stuff. And once again, as you can see, a lot of the summation terms have not been included because Einstein dropped a lot of the stuff. So he just wanted it pretty simplistic. He didn't want billions of sigmas everywhere in the equation, so he kept it pretty simple. This, as you can see, is the Einstein tensor, which, as we know, which basically equals this when we're having a zeroed out cosmological constant. Now that might be an interesting question or interesting idea. What do you mean by zeroed out cosmological constant? When we're working with stars, when we're working with planets, black holes even, the cosmological constant doesn't necessarily have to be included because we're only talking about the body in reference. When we're talking about the universe, when we're talking about the galaxy, then the cosmological constant has to be included because we're actually talking about a certain expansion or a certain scalar multiple of the metric tensor. So it's being expanded by some amount which the cosmological constant takes care of. So this right over there is a Ricci scalar. I didn't really include it because a Ricci scalar is simply a scalar version of this. So we have this in a tensor version, which is, as I mentioned, a matrix. So making a matrix a scalar quantity is simply what that is over there. As I mentioned, the Einstein tensor. And then we're getting into one thing that I said I will explain. This is the stress energy momentum tensor. Now, the actual elements of the stress energy momentum tensor, for some reason, has been debated over the internet because I couldn't find an actual value of which values are which. There were various different sources. I want to come up completely honest with you because I don't want to start lying and saying that this is this, this is this, because there were various different sources online that told me completely different things. But I'm going to go with this because this is what a professor taught, and I hope that this is really what he's trying to say. So, we have t sub 0, 0, always, that's always working with the time coordinate. These are the energy flow coordinates. Once again, this is the stress energy momentum tensor. So we're working with everything. We're working with the stress. We're working with energy, everything. These right here are the momentum density. Once again, this only applies when we're working with gravity. Now that is where Einstein's field equations can be taken a step further. Gravity doesn't only have to be the only thing. We can even have light. So instead of the stress energy momentum tensor, we can be working with the 4 vector, which is a simple vector. And what that actually proves, this is extremely important to understanding the properties of the graviton, which I'm going to be coming into in the end. So 8 pi g over c4, once again, if you want to know, if we have time, I will be explaining it. I actually have a derivation of it. If you want to know why it's 8 pi g over c to the 4th, don't worry, that'll all in the explanation. Okay, any questions by the way? If you want to understand this a little bit better, you can think of a simple analogy. For example, because many people wonder, sure, you can find the curvature, but man, just get to it. How is this related to gravitational waves? A lot of you might be in your head, like, how is this related to gravitational waves? That is where this once again comes into play. As I mentioned, this can tell us the curvature of the manifold. How can that help us? Let me give you a simple example, a simple analogy. Let's say we have a 2 kilogram ball on a trampoline, and then we have a 20 kilogram ball on a trampoline. We all know that the 20 kilogram ball will make a higher or a larger indent. That's your answer. If we measure the indentation, or in this case the curvature of that trampoline or the manifold, we can actually measure the energy that that ball has, or in this case, the gravitational energy. And that is really how and why this is used to calculate gravitational waves, and why it's so important that we prove this in 2015 at LIGO. Using these equations, we predicted some version of an amplitude, some version of a frequency, and that is sort of similar to what we got. Obviously not exactly, because there is some uncertainty in every single equation that we do when we are not directly near the apparatus. But really understanding what this is and how gravity can integrate into this entire equation is really important. So now, as I mentioned, we're going to be getting into these, the Christoffel symbol. Yeah.
So basically, what we're measuring is the curvature, and then we measure the gravity.
Exactly, because the curvature.
We first measure at the energy, and then we measure gravity, or we measure energy first?
We first measure the curvature of the manifold,
Alright.
and that will tell us the energy that it actually has. Thinking about that simple ball analogy once again, right?
Alright.
20 kilogram will make us bigger indentation.
Good example.
And if we measure that indentation, we can say, hey, listen, this might be a heavier ball than the 2 kilogram one because it has a higher indentation.
Right.
So that's really what the curvature is used for. And that's why it's so important to really understand how space itself is curved. Now, as I mentioned earlier on, and you might have been really wondering about that Newtonian mechanics is not wrong, and it really isn't. Because, for the round of applause, the field equations break down into Newtonian mechanics when we are talking about low gravity and low speeds. Now this is where stuff gets really interesting. Because we have, the Christoffel symbol over there, which is equivalent to the force of gravity. Now, who could have thought of that? Now, this is very important because this is literally how we proved the stress energy momentum tensor. Using this analogy, once again, I can explain it in the end if you want. Using this analogy, we understood what the Christoffel symbol was and how it equates to the force. From here, we deduce the stress energy momentum tensor. In Newtonian mechanics, as you can see over here, we are equating it to only the time coordinate of the metric tensor. This is because of a simple reason. Once again, as we know, when we're talking about Newtonian mechanics, we're talking about low speeds, we're talking about low gravity, no black holes, no photons, no singularities, nothing like that. We're talking about a simple apparatus like a spacecraft orbiting Earth, not a very complex apparatus. So there's only gravitational field from the Earth, very minute from the Moon, but that could be discarded. So this is what it breaks down into, because all the other partial derivatives of the other versions of the metric tensor, which is right here, basically breaks down to zero. Obviously not exactly zero, but could be excluded. Many times when you take things to infinity or take things to zero, we just assume that it's going to infinity, so we cancel out the entire term. That's basically what's happening over here. Now, d phi over there, phi is the potential energy of our system. As I mentioned, let's say we have, let's say we have a field, we have our potential energy of the field, our potential of the field, depending on what it actually is, and that's simply, I'm just equating the force over there over any simple field, and that's going to be Newtonian mechanics. And this entire Christoffel symbol over there is deduced from this ideology. So this over here, now this is a pretty complex derivation, which will take a long time, but just understanding what's really happening over here, once again, can be explained pretty simply. So these, once again, are the summation terms, which I have excluded in this situation because it just would be too much, where gamma is the summation term. Right there, gamma, where you're basically seeing gamma everywhere, and you're subtracting, as you can see, the last partial derivative when you are differentiating with gamma. That's a very important aspect to remember, that we are actually subtracting it when differentiating with gamma. So, this is basically a whole bunch of stuff where you can actually see the difference between a contravariant tensor and a covariant tensor. This is once again where my explanation kind of makes sense on the contravariance and the covariance, when we're looking at the difference between when a contravariant tensor is used and when a covariant tensor is used. So hopefully you guys kind of understood that. So now we're going to be getting into, I do realize that I am running out of time, but I do have some time, so we can now start talking about the last possible thing, which is really amazing, the first proved solutions for the field equations. The Schwarzschild metric. This is really interesting because this might seem interesting. Now remember I was talking about Pythagorean Theorem? Yeah. This is exactly that. Okay. So this is basically Pythagorean Theorem and how it conforms in the manifold. As I mentioned earlier on, the entire idea of curvature is Pythagorean Theorem and how it conforms with respect to the manifold. And this is exactly that. Don't worry, I'm going to be explaining the variables right here. But what we actually have is a curvature, which this is measuring. So Pythagorean Theorem, or ds squared, equals some version of curvature. And that curvature is the Schwarzschild metric right there. So c squared, as you might know, it's speed of light. Then you get the tau, which is proper time. Tau is very important, because that, as I mentioned, is proper time. Proper time is basically a situation when the inertial frame of an external observer is equal to the inertial frame of the source. Obviously excluding photons. This does not include photons, by the way. Because photons can never be speed of 0 in any inertial reference frame, and because of that, this does not apply to photons. So what proper time really means is, let's say I'm moving at some velocity, let's say 100,000 meters per second, I'm moving pretty fast. You will agree on a different time, you will agree on a different time, because all of our times are relative. However, proper time is another external observer relative to the source, right? An external observer, but traveling in my inertial frame. Or scientifically speaking, it's called following the world line. So all observers can agree on this time, because it is an external observer, so the source isn't lying to anyone, but that external observer is at rest with respect to the source. Any questions? Yeah.
When you say at rest with respect to the source,
Sorry.
you say at rest with respect to the frame of reference. Does that mean that he's within that same field of reference?
Yes. So basically what that means is, let's say I'm traveling at some certain velocity, as I mentioned, 100,000 meters per second, and you are traveling at 2 and he's traveling at 10,000, whatever. All of our times are going to be different because, as I mentioned, as you know, time is relative.
Yeah.
However, what proper time means is another person, an external observer, traveling in my frame of reference. What that means is, with respect to me, he is traveling at 0 meters per second, which is exactly why this does not work with light, because light can never travel at 0 meters per second in any reference frame. So this works with everything but light. So, defining the variables, Rs is the Schwarzschild radius, which is the radius at which any object, even you and me, can become black holes. The Earth, by the way, is 8.6 millimeters for it to be a black hole. No, wait. Yeah, the radius is 8.6 millimeters for the Earth to be a black hole, plugging it into this equation. Technically, this equation should be less than, because the escape velocity in the black hole is greater than the speed of light, so it should be less than, but this is what generally people talk about because it's sort of in the same vicinity. R theta phi is simply polar coordinates, because that's what's used very often when we're talking about spherical coordinate systems. T is the time and dimension, c is the speed of light. Now, what this proved is very interesting, because just a few months after Einstein's theory was released, Schwarzschild gave him this paper. Now, what's really interesting to see is that Schwarzschild, yes, he did exclude a lot of the very important things. He said there's a zero cosmological constant. He said there's no electric charge. He said there's no angular momentum. So yes, he did make a lot of assumptions, but as we know, today that object is called a Schwarzschild black hole. A non-rotating, no electric charge black hole, which basically is not very common, but it's still there. And that's what a Schwarzschild black hole is. And this proves that. So now you might be wondering why. Why did I actually show you this? Yes, because it's the first proved field equations, but more importantly, because this showed Einstein something very, very weird. This showed the entire physics society something very weird. This proved that there was one region in space where the curvature was infinite. Now that doesn't make any sense, right? I mean, how can you even visualize infinite curvature? But as we know now, he was talking about the singularity, where there is infinite curvature, where things are just weird. Black holes themselves are so weird, they have a way to actually violate the laws of physics without violating the laws of physics. If you have heard of the Pauli exclusion principle, which says that two electrons can never be in the same quantum state at the same time, black holes technically should be doing that, right? Because they're so squashed together, two electrons should definitely be in the same quantum state. However, because space is so weirdly curved, they actually violate those laws without violating those laws. So it's really interesting. And that's why black hole physics, astrophysics in general, is a really interesting topic to see. So a naked singularity would really be an amazing observing, if it is possible, an amazing achievement, because it would prove a lot that we know about Einstein's field equations, and generally speaking, what and how does a naked singularity look like? Any questions? Okay, so now hopefully, if you were really bummed out by the math, don't worry. Now, if I'm not mistaken, there is no more math for those people that don't like it.
Why were they so confused that space's curvature could be asymptotic towards position?
Because when you're talking about 1916, they didn't really think about infinite curvature. Sure, you can measure or you can think of an infinite line going forever, but how can you think of infinite curvature? How can you really visualize that? So in the beginning, yeah, but when you're, okay, 1916, you have to think of that variation in where infinity itself was a kind of a lost concept, where when you're talking about curvature, remember, this was just a few months after Einstein's field equation. That's very, very, very commendable. Unfortunately, Schwarzschild actually died a few months after this. Sorry. He actually died a few months after this, and therefore it's really good that he actually submitted these papers. But what's really incredible is that just a few months after releasing maybe the most famous equation in the world, or, okay, equivalence squared is a little more famous, but maybe the most important equation in the world was solved in just a few months. Even Einstein he didn't solve it. Well, Schwarzschild did, and what he proved, as I mentioned, was infinite curvature, which at the time was a little bit weird. Sure, they could deduce something out of it. They could deduce that there is this version. Sure, it might be wrong, but then they rechecked it. Okay, it starts to make a little sense. We have to call this place something, and that's what we call a singularity.